Hello everyone, my name is Kushijan and my topic is motion on a plane and the central orbit with its application of Kepler's law. Motion of a plane curve. Motion on a smooth plane curve. We have a smooth plane curve. Let us suppose the position of a particle on the curve at a time t be p x comma y with arc length s. This arc length s measured from a fixed point p1. Let v be the velocity at p, and x comma y are the components of a force acting on a particle along a coordinate axis. X y be the component of a force. A normal reaction R act at P on a particle because the curve is smooth. On resolving the force along tangent at P, the motion is given by mv dv upon ds is not equals to x cos psi plus y sine. If we put this equation 1 now, but cos psi from this figure we can conclude that a cos psi is equals to dx upon dy and sin psi dy by ds. Then we have mv dv upon ds equals to x dx upon ds plus y dy by ds. Since cos psi and sin psi, we have a value dx upon ds, dy upon ds. Now integrating with respect to s, we will integrate. Then this part and this part will be cancel out. So we get this half mv square by integration, and this integrating x dx plus y dy plus c1. C1 is the integrating constant. This we put this equation as 2. Let us take x dx plus y dy equals to phi x comma y. We put this. Now since we have x equals to del psi upon del x, this is del, and y equals to del psi upon del y, then we have this. We put this in this equation 2, we get d psi, and we get 2, and 2 will be come in this with this constant. Half mv square equals to psi plus c1. Half mv square we get this and c1. Now here psi x comma y is known as a work function. It is known as a work function, and half mv square is known as kinetic energy of a particle at p x y. Let initially the particle of a mass m start the motion with a velocity v naught from a point p1 x naught y naught. Then equation 3 gives half mv naught square equals to this is equation 3. From this, if initially mass m and this starts with velocity v naught, then we have this we put this equation as equation 4. From 3 and 4 we have, since we equate that v minus equation 3 from equation 4, we get this equation. We put this equation as equation 5. The RHS of equation 5, the right hand side of equation 5 shows the work done in the moving the particle from p x naught y naught to p x comma y. This shows. Whereas the LHS shows a change in the kinetic energy of a particle. This is called change from kinetic energy. So the change in a kinetic energy is equals to the work done of a total external force. The equation 5 of an energy equation and the force of this type is known as a conservative force. This type of force is known as conservative force. The potential energy of a particle in a position px comma y is equals to the position px comma y equals to the work done by the force when the particle moves from px comma y to the new standard position x dash y dash. We have this potential energy at p is x comma limit from x comma y to x dash y dash x dx and y dy. Now we put this as limit and we get this. We put this equation as 7, but we know that a kinetic energy is given by half mv square. We have from 3 we can conclude that. Now adding kinetic and potential so we get a total energy, this psi x dash y dash plus c1, which is kinetic energy plus potential energy is constant. Now what is a central orbit? Firstly, we talk about the central force. A force which is always directed towards a fixed point is known as a central force. The fixed point is known as center of force. Now, what is a central orbit? The path described by the particle under the action of central force is known as a central orbit. Now, a differential equation of a central orbit is: a particle moves in a plane curve with an acceleration p, which is always directed towards a fixed point O in a plane. To derive the differential equation of this path. Now, what is a polar form of this equation is, we have to suppose that let a particle be at a r comma theta at any time t, point O, that is pole is the center of force. The acceleration p acts along AO. The acceleration is a radial acceleration, so there is no transfer component of the acceleration. Then we have a d square r upon dt square minus r d theta upon dt whole square minus p ra, which is similar to the r dot, and which where r double dot means r square d theta d upon d, and theta dot means d theta upon dt. This one. Now, and 1 upon r d upon dt, r square d theta upon dt equals to 0. This. After integrating, we have r square d theta upon dt equals to h, where h is a constant. We put this equation 3. Put r equals to 1 upon u and differentiate with respect to t. We get dr by dt equals to minus 1 upon u square du by dt equals to minus 1 upon u square du upon dt d theta upon dt. We can write this as this also. Dr by dt equals to r square, since 1 upon u is equals to r, so there is a r square d theta upon dt. We put this and we get this, where from equation 3 r square d theta upon dt is h. Again differentiating with respect to t, we get this. Put this equation as a 4, putting the value of d square upon dt square and d theta upon dt in equation 1. So we get this, and h square u square d square u d theta square plus u equals to p. This is equation 5, which is a polar equation form of a differential equation of central orbit. Now next is application of a Kepler's law using equation of central orbit. So from Kepler's second law, the imaginary line joining a planet to a some sweeps equal area and equal, this is sun, equal area and equal interval of a time, that is area and velocity remains constant. Proof: let the planet be at a r comma theta at a point time t. The point O, that is pole, is a center of force. If a particle moves under a central orbit of a force, that is a trajectory, is known as a central orbit. The equation of the central orbit is given by r dr square by dt square minus r d theta by dt equals to minus fr, which is the equation 1. Then 1 upon r d upon dt r square d theta by dt equals to 0, equation 2. From equation 2, this is 0. R square d theta by dt equals to h, where h is a constant, which is equation 3. Now we know that if we want to write area of a given curve is written as dA upon dA equals to 1 upon 2 pi square dt d theta. dA equals to 1 upon 2 pi square d theta. From equation 3 r square d theta equals to h d dt. dA, this is dA equals to 1 upon 2 h dt. Then dA upon dt equals to h by 2, where it is a constant, since it is a constant. Hence the aerial velocity is a constant. Kepler's second law is proved. Thank you.